All right. Okay. So thanks a
I'm
lot.
sorry.
Let's indeed start the next session. So my name is Alexander Tsirlin, and I work at the University of Augsburg in Germany. And today I wanted to tell about our recent work on quantum spin liquid candidates in a terbium-based triangular antiferromagnets. So compared to my initial abstract, it will be a bit of a broader overview because there were things that happened in the last 1.5 years, not only the bad things like the pandemic, but also the good things like the new research. And I will try to give you a bit of a summary of where we are now with all these projects. But first of all, let me explain what the quantum spin liquid is and why we are looking for this exotic state so actively. And let me say that nowadays there is a lot of interest in quantum materials, also at this conference, but in general, the quantum materials are something that is very hard to see, something that I would call not really tangible, because typically it's some two-dimensional electron gas or some complex structures of atoms or something like that. But in fact, there are also some very easily recognizable quantum materials around us, and one such material is definitely known to everyone who is working with low-temperature physics. It's the example, basically the only example of a quantum liquid, which is helium, right? And I guess all of you know the differences between helium and any kind of ordinary liquid. So the ordinary liquid is supposed to freeze below a certain crystallization temperature, but if I take helium at ambient pressure, it doesn't freeze, and moreover, it goes into an exotic quantum state where helium becomes superfluid. So we can think of a very direct analogy between this behavior of ordinary versus quantum liquids and the behavior of magnets, right? Because in magnets, we also have some sort of a crystallization transition. That's the magnetic ordering, where our magnets transform from the paramagnetic state to the ferro or antiparamagnetic state. But then if we put some additional quantum effects into the magnets, then perhaps we can suppress this magnetic ordering transition and reach the situation when down to zero temperature, the magnet remains disordered but strongly correlated. And that's basically what we call, at least on the most basic level, spin liquid. So the collection of spins which do not show long-range order, which don't show any symmetry breaking, but which fluctuate, but which at the same time remain strongly correlated. There is some sort of short-range order, but no long-range order. And if such a state is realized, and it can be realized at least on the theory level, then it is supposed to have many interesting properties, like it can be the parent state for superconductors, is a strongly entangled state that can be used in quantum computing and so on. But the question is how to really get there. So how to make a magnet quantum. For this, we again have a very direct recipe from the theoretical physics. It tells us that as we reduce the size of the spin, then it becomes more and more quantum, right? Because if I take spin 1/2, it can have only two projections on the quantization axis. So there is clearly a very strong quantization effect. But if I go to the large spin, eventually to the infinite spin, then any projection is possible, and then the large spins behave classically. So I definitely need the low spin. I need spin 1/2. But this is actually not enough, because if I just take a spin 1/2 atom and construct an antiferromagnet out of the spin 1/2 atoms, then it will be still magnetically ordered, and the excitation will be pretty much the standard magnet. So that won't be a spin liquid yet. We need the second ingredient, and the second ingredient is the frustration, the effect of competing exchange couplings, for example, on a triangle. So if I treat frustration alone, if I, let's say, put classical spins on this triangle, then they're still going to show some kind of magnetic order, this 120 degrees order. It's like not perfect for any of them, but it's good enough so that they can gain some additional energy from this kind of non-collinear ordering, right? So that's a sort of compromise configuration between being up-down. So all of them lose some energy by being non-collinear, but still gain some energy by aligning at 120 degrees relative to each other. But if I now take this triangular system and put some quantum fluctuations in, so basically if I create these triangles using spin 1/2, then the situation can be more interesting, because in this case, it is predicted, and it's actually nearly 50-year-old prediction by Philip Anderson, that a qualitatively new state called resonating valence bond state can form. So what happens here is that the three spins on the triangle, they cannot be all antiparallel at the same time, but they can form this up-down pair and then leave the third spin behind, right? So that's basically what happens here. But the third spin is, of course, not very happy about it. So at some point, it will claim its rights, and then it will try to form such a pair with one of the other spins. So basically what will happen is that this spin singlets will be fluctuating all over the lattice. So at some point of time, it will be here. At some point of time, it will be here, and so on. And the overall ground state will be a kind of collection of these different spin singlets arranged on the triangular lattice, right? So because of the close similarity between this up-down state and the chemical bond, this dimer has been called the valence bond, and then the overall spin liquid ground state is the so-called resonating valence bond ground state because it combines the different arrangements of these dimers on the triangular lattice. So that's what was predicted in 1973. It is still a bit debatable whether this state was ever seen experimentally, but I will show you today maybe the best possible approximation for such a state. But first, let me explain why we are so interested in this state, because of course it is exotic, but at first glance, it doesn't seem to have any clear implications. But the implications become more transparent when you look at the possible excitations out of this state. So how the excitation look like? We break one of these dimers, and then we create the two unpaired spins, right? The two spins that are both up. But then it turns out that these two up spins don't have to be fixed on the lattice, so they don't have to sit always at this place, but they can move around independently from each other. So one spin can go to the left, the other spin can go to the right. And they will be perfectly fine about moving through this triangular lattice without really taking care of each other. So we start with the excitation that carries spin 1, right? So that's the integer spin, because we break one dimer. But then it breaks down into two independent spin 1/2 excitations. And this is the effect that is called the fractionalization. And that is the kind of effect that is characteristic of a very unusual structure of the underlying ground state. So when such fractionalized excitations appear, it means that our ground state is strongly entangled, like, for example, the ground state of the two-dimensional electron gas or the fractional quantum Hall effect. So over there, we have the entanglement due to the strong electron interactions. Here we have the entanglement due to the quantum effects and magnetic frustration. So the easy way to understand this entanglement is the following. So that's the analogy from Professor Venn in his recent review article in Science, that basically we can have different types of collective behavior of the particles in such entangled systems. He calls this the choreographed dances. And these choreographed dances are obviously can obviously be quite interesting both from the aesthetic perspective and also from the underlying physics. So what can be the consequences? One consequence is that if I have a state with fermionic spin 1/2 excitations, it can be a natural precursor of a superconducting state. That's the idea that was most actively developed by Anderson, also in the context of high-TC cuprates. The second idea that became obvious only more recently is that these fractionalized excitations can also serve as the basis for topological quantum computing, and this is what many groups are trying to work now to actually tailor these excitations in different systems, not only in magnets, but also in superconducting nanostructures, in order to be able to achieve new platforms for quantum computing. But if we go back to our spin liquid story, then there can be many interesting implications. The spin liquid state is interesting, but we need to know how to realize it in the lab, how to get the good material that shows this kind of behavior. And that's what I'm going to present in the rest of my talk, our attempts to search for such triangular materials where this state or some other spin liquid state can be realized. So this is the first candidate material that came to our attention already 6 years ago, 2015. And this material is closely related to Yusheng Li, who was the postdoc in our group and who basically brought this material from his PhD study where he discovered it. Now Yusheng already became the assistant professor at Wuhan, and well, all of you know, I'm sure, where Wuhan is and what is the significance of this place. I can tell you that Yusheng went there shortly before this whole thing started in the middle of 2019, but we're pretty sure that he's unrelated, and he actually also suffered a lot from all the disruptions in the research caused by the pandemic. But anyway, so this is the material. It's actually pretty simple crystal structure. We have the ytterbium-3+ as the magnetic ion. And at low temperatures, it can be described as an effective spin-1/2. So we have the strong quantum effects that we need to create a spin liquid. These are the triangular layers, and they're separated by the slabs of magnesium and gallium, which are non-magnetic. So we have the very good separation between the magnetic layers, and we seem to have a suitable platform to create a spin liquid state. Well, how do we know that this material has a potential to show the spin liquid behavior, that this material is different from like any other antiferromagnet? First of all, we measure specific heat because specific heat is a good probe of the possible phase transitions. And here you see the specific heat measured down to 50 millikelvin, and you see that there is a broad hump, but no anomalies, which means that there should be no magnetic long-range order, and indeed, this material is a strong candidate for the quantum disordered state because this temperature of 50 millikelvin is about 5% of the exchange coupling. So indeed, all over this range, the spin should be correlated, but should not develop any long-range magnetic order. And of course, we also confirmed it by MUSR and by other techniques that there is indeed no long-range magnetic order in this material. But as I told you before, the main draw of the spin liquid state are its unusual excitations. So we want to probe the magnetic excitations, and in fact, we can gain some insight already from the specific heat data. Because specific heat at low temperatures typically shows some kind of a power law behavior. For example, if the specific heat is due to phonons, then it should be T cube. If we have magnets in antiferromagnetically ordered state, it will be T squared or T cube, depending on the dimensionality. But if we have the linear or sublinear behavior, that is quite unusual for magnets. Well, of course, it's not unusual for metallic systems because the metals also show the linear contribution to the specific heat. But this compound is a very robust insulator with a band gap of maybe 4 eV. So we for sure do not expect any electronic contribution. But if we see something linear or sublinear in the specific heat, it immediately indicates the unusual magnetism. And in this case, indeed the power law was quite unexpected. We got the exponent of about 2/3, 2/3, so the sublinear behavior. And that was the first indication that some fermionic-like excitations, some fractionalized spin excitations like shown here, in the upper part of the slide can take place in this material. Then, of course, you want the more direct probe than just looking at the specific heat. So you go to the neutron scattering, and then you realize that someone else already did it. That was the case for this compound, where the Chinese group led by Jun Zhao published this Nature article in 2016. And they measured the magnetic excitations at very low temperatures and very low energies. And if this material were anything conventional like the antiferromagnet, then they would just see the spin waves, so they would see just some points in this energy cuts. But instead, they saw the broad distribution of the scattering intensity, which is again typical for this fractionalized excitations. And they could even reproduce it quite well using a simple phenomenological model, which made them to come up with this claim of the spin and Fermi circles in the triangular quantum spin liquid candidate. So that was all fine, and it seemed like the good material is already there. But the problem was that this description was purely phenomenological. So it was not really clear what are the interactions that drive this behavior. And that's what we tried to figure out. So how do you do it? Well, when you have this continuum of spin 1/2 excitations, you cannot really do much with it because it's so broad and sort of uncharacteristic. So what you do, you try to polarize your system, apply the magnetic field, right? In this case, you need around 9 Tesla to reach the fully polarized state. And then you know that all your spins should be just aligned parallel to the field. So you get a ferromagnet. And with a ferromagnet, we know how to deal because the standard linear spin wave theory should be sufficient to describe magnetic excitation. So in this state, around 9 Tesla, we expect the simple spin wave excitations. Then we go and measure them with inelastic neutron scattering. And surprisingly, we don't see anything that really looks like spin wave dispersion. Well, basically, we see still a very large blob of intensity. You can try to put some spin wave dispersion in here, but that pretty much is not the normal spin wave. All right, so for some reason, even at the fully polarized state, which should be ferromagnetically ordered, we still see a very broad dispersion. Why could it be? One possibility is that there is some underlying structural disorder that leads to the random magnetic couplings. And we tried to explore this scenario further. Indeed, when we did a careful structural study, we have seen some unusual feature. This is the atomic displacement parameter of terbium. And you see that even at low temperatures, the ellipsoid is very asymmetric, which is strange because the terbium is sitting in the ideal octahedron, so the vibrations of the terbium should be symmetric, but they're not. Then we tried to connect this effect to the electronic structure of the terbium 3+. And here, let me remind you how it generally looks like in these 4F compounds, that if I have just the single terbium 3+ ion, then it is a J7.5 multipled. Then I put the terbium into the crystal environment. I have the crystal field from oxygens, and it splits the multipled into 4 crystal field levels. And this lowest Kramer's doublet should lead to the spin-1/2 behavior, effective spin-1/2. But if I had the structural disorder, so if I assume that the terbium is not sitting maybe exactly in the center of the octahedron, but moves a bit up and down, then these crystal field levels should be broad. And that's exactly what we saw in this material when we went to look at the crystal field levels with inelastic neutron scattering. So here you see the experimental pattern, and you see that all 3 peaks are much broader than the instrumental resolution, and there is even some additional shoulder which should not appear in the normal terbium case. Eventually, we were able to reproduce this picture quite well. I won't go into details, but I will only try to give you the general idea why this disorder effect takes place and where it comes from. So you may remember that the crystal structure, we had this magnetic layer of terbium, and then we had the slabs of magnesium and gallium in between the magnetic layers. And magnesium and gallium are mixed. So each of these positions is actually randomly occupied by both magnesium and gallium. At first, we didn't pay any attention to it because, okay, that's non-magnetic, so who cares? But in fact, they have the different charge. So magnesium is 2+, and gallium is 3+. And it seems to be important because if I imagine that I have more magnesium on one side of the layer and more gallium on the other side of the layer, then I create some clear charge misbalance so that there is less positive charge on the top and more positive charge on the bottom. And then I can imagine that the terbium will move towards the less positive charge, and oxygen will move towards the more positive charge. So this will cause the deformation of my magnetic layer. And these deformations are actually quite significant. About 0.1 angstrom are the typical displacement here. And when you include this, then you can reproduce the experimental crystal field excitations quite well. So we do have a lot of structural randomness in the system, and that has its implications for the magnetic excitations. Because when we looked at these low energy excitations in more detail, we actually were able to describe them with 2 different terms. One of them are these generic excitations of the quantum spin liquid, so the breaking of the singlet into 2 spinons. But on top of that, it turns out that there are some unpaired spins present down to lowest temperatures, and they can change places with the singlets, and this is what dominates the low energy part of the spectrum. And basically, when all this data started to appear, there was also the very nice theoretical development by Itamar Kimchi and his colleagues, who showed that you can get this kind of quantum soup, the mixture of unpaired Orpan spins and spin singlets, making the quantum disordered state that arises from the structural disorder. So in a way, we got something that looks rather similar to a genuine spin liquid, but it is driven not by frustration, but by this structural disorder and the randomness effects. So we got a potential spin liquid candidate, I would say, but it was not the best one. So then how to improve it? So we know that the whole problem came from this interlayer space where we mixed magnesium and gallium. So we shouldn't mix them, we should replace them with something that has the uniform charge and shows no random distribution. Mm-hmm. And one possibility is to put the just the sodium atoms, and then we come to the compound sodium YbMgAO2, which actually has been known since a long time, but nobody ever paid attention to it because it is one out of 100 compounds with this rock salt type crystal structure, and at first glance they all look the same. So this part of the work I really owe to Lei Ding, who was at some point a postdoc with us, then later at Oak Ridge, and now he's working at Institut Nel in Grenoble. I should also say that after this was published, we did quite a lot on the similar sulfide and selenide compounds, which can be prepared as single crystals in contrast to this oxide. But today, let me tell you more about the oxide, because this sulfides and selenides work is still a bit of a work in progress, but for the oxide, we understand quite well what is going on. So first of all, we wanted to make sure that the structural disorder has been eliminated, that the material is well structurally ordered. We already know that we should look at the crystal field excitations, right? So we expect 3 resolution limited peaks due to these excitations. That's what we tried to measure on the sodium YbMgAO2, and indeed we observed exactly what we expected. So in the previous case, we had these very broad peaks, which were much broader than the instrumental resolution. Now we have 3 resolution limited peaks and no additional features like this one. So indeed, we have no structural disorder in the sodium YbMgAO2. Now let's see how it affects the low energy excitations. Again, the first probe is the specific heat. In the previous compound, we had this unusual sublinear behavior, which was initially interpreted as spin and excitations. In sodium YbMgAO2, it actually looks rather different. So if we measure it in zero field, then there is no power law behavior at all. You see that this black curve doesn't show any straight line in the double log coordinates. But if we apply small magnetic field, then we get to a very clear t-squared behavior, which, well, can have different interpretations. So basically, when we see the t-squared behavior, we know that it's a 2-dimensional system with a linear dispersion. So the excitation should be linear in K, and the system should be 2-dimensional. And there are 2 possible explanations for that. One is, let's say, more exotic, that we have the so-called Dirac spin liquid. So the spin liquid with the linear excitations coming out of the Dirac point, just like in the electronic topological materials. And the second, more trivial explanation is that we have the simple 2-dimensional antiferromagnet, we have 2-dimensional spin waves, and they cause the t-squared behavior. Well, of course, you see from the specific heat that there are no phase transitions, so it can't be really the well-ordered, like long-range ordered antiferromagnet, but maybe there are just strong 2-dimensional correlations, and they drive the t-squared behavior, but there is no unusual entangled state like a spin liquid. So right now we actually have the possible evidence for both of these interpretations. So the evidence for the Dirac spin liquid comes again from the inelastic Neutron scattering, where we look at the distribution of the intensity in the reciprocal space. You see that it's actually different in the compound with the structural disorder and in the structurally ordered compound. We have this hexagonal brilliant zone with the K and M points, and for YbMgGaO gallium, the intensity accumulates at the M point of the brilliant zone. For the sodium YbMgAO2, the intensity accumulates at the K point of the brilliant zone. So that's the clear difference between the 2. And if we now look at the theoretical prediction that you see here, so the Dirac spin liquid for some triangular spin model, then the intensity is expected to be at K and not at M. So indeed, for the sodium YbMgAO2 compound, we have the intensity of the low energy excitations sitting at the position where theory expects it. So this was the strong evidence for the possible Dirac spin liquid state in this sodium ytterbium O2. On the other hand, we cannot really exclude the importance of just the pure two-dimensional order in these systems. And in the last couple of minutes, let me explain you why. So the reason is that in all these materials, the triangular layers are displaced with respect to each other, right? So they are displaced in such a way that each ytterbium ion interacts to 3 ions of the neighboring layer, right? So they're not stacked perfectly on top of each other, but there is a shift, and therefore there are several interlayer couplings like that, and they obviously are going to cause some interlayer frustration because these 3 couplings cannot be satisfied at the same time. And in fact, this is a very common situation that you encounter in many different types of layered materials. But I think it's still not so clear how it affects the magnetic order, especially when you have the triangular planes and the frustration. And we tried to see it by going to the more classical system, to the chromates, which can also form the same type of crystal structure, because then we kind of remove the quantum effects. We do not expect really a spin liquid, but we can just see how this interlayer frustration impacts magnetic order. And that's what we did in collaboration with Ramesh Nath and Philip Mendels, studied a couple of these chromate compounds, the hydrogen chromate and sodium chromate. And we saw actually a very unusual behavior, which is also universal across this whole compound family. So if you look at the specific hit, then you would think, okay, there is just the standard boring magnetic order in here. But if you start to look locally, for example, at NMR intensity or at the muon spin rotation, then you see that there is a quite extended regime going to around 70% of Tn, where the system seems to have the pure two-dimensional spin fluctuations. So the interlayer order does not develop down to this point, and only below this temperature the different layers start to order. Also in neutron scattering, there is evidence for the same kind of behavior. And that's why we think that the interlayer frustration can really seriously affect the three-dimensional long-range order. So when you have these shifted magnetic layers, then they may have some problems to order. And then you may have the situation where there will be magnetic order within each plane, but there will be no macroscopic long-range order. So with this, I come to my summary. I tried to show you that, well, getting the spin liquid states in the lab is possible. We do have some candidates. We do have systems with unusual excitations, but we still have to be quite careful in distinguishing the true origin of this behavior, because it can be the structural disorder. It can be different sorts of frustration, including the frustration by interlayer couplings, which is usually neglected in many theoretical studies, but that may be important in the real materials. And with this, let me thank the organizers for the opportunity to be here, at least remotely, and also thank you for your attention.
You talk about the disorder, but disorder, this is a dynamic disorder or static?
In this case, it is static disorder, because
this is static one. Okay.
Yes, this is the static disorder. At least that's how we understand it. Because so if you measure XRD down to low temperatures, you will see that the displacement at ellipsoid remains anisotropic. Even at low temperatures, even at 100 Kelvin, it's very much elongated.
I see. Then I have second question. Then do you how was the effective moment at ytterbium side? This is obviously pure ytterbium 3+ state for both compound?
Yes. So it is ytterbium 3+ from all the measurements that we have.
I see. The other comment or questions?
There is also a question in the chat, so maybe I just read it. For the sodium compound, do you have indications from MUSR for a disordered versus ordered ground state? So for the sodium compound, we did MUSR, and there are no signatures of magnetic ordering, like there are no oscillations in the spectrum. There are some features which are not entirely clear to me, like there are 2 relaxation rates for some reason. which is something that people see rather often, maybe at different stop sites or something. But yeah, so this is one like peculiarity that we saw in the MERSAR, but certainly no static fields.